Okay, so I think I should start here. Okay, so next is so last class we talked about the current design practice, but this is something the one which is upcoming, and the IS 1893 being revised, and by next year you would have the performance-based design as one of the core as a different section of your IS 1893. So the first question is, since we have a design practice, why do we need the seismic design following a different approach, which is performance-based design? So the basic design philosophy is like whatever the demand you calculate, or the base shear or the lateral forces, as a whole, the structural the structure is subjected to some kind of design force. Each member or as a structure of whole, they should actually resist the that load safely. But what is the actual problem here is how good your analysis is and how well you have defined the loading. For example, like whether your equivalent static force method, based on which you calculate the design base shear, is really take care of the expected loading or not. And at the same time, you have to your design need to be economical, and it must actually satisfy or fulfill all the objectives. The first question actually arises from this seismic earthquake resistant design. What are my performance goals? That means I am designing structure, so what I am expecting from a structure when there is an earthquake? The basic answer to this is I don't know, because I am designing a structure based on elastic concept. If you follow IS 456, IS 1893, IS 800, for the design, you have two mother code, IS 456 for concrete and IS 800 for the steel. So you have 0.87 FY, or your partial safety factor FCKY, gamma. That means all your design is linear. What you are expecting during an earthquake is a nonlinear behavior. So what is the guarantee that if I follow the current procedure, I will get expected behavior? So the current codes are mostly prescriptive. In the beginning of the last lecture, I said that there are some earthquake intensity: minor earthquake, moderate earthquake, major or severe earthquake, and which are mostly defined by frequency of occurrence. Like the minor earthquakes are more frequent, major earthquakes are very rare and unusual. And I defined that no structural damage or limited structural damage or no collapse. Now, if somebody asks me, like, what is the definition of the minor? What is the meaning of frequent? For example, several times, how many times? And limited damage means, what is the definition of the limited damage? And all these things I'm doing following a response spectra which is unique. I have one response spectra. So these are the some terms which are actually not quantitative definitions. If you just summarize the current code procedure, it simply calculate the design base shear and divide a factor called R. In a sense, if let's say this is my design spectrum, you multiply Z, SA, whatever it is. What essentially you are doing is you are actually reducing by, R by I, right? And then you are getting a response, and based on this response curve, you are designing. Now, how to ensure that your strong column, weak beam philosophy will be satisfied when there is an earthquake? How to ensure that there will be no collapse? So, is there a guarantee that the low, the current provisions which are following for the seismic design is good enough? Now, second question is, what is the definition of minor earthquake? What the code actually intend that the minor earthquake is something which has a written period of the event which is written around 100 years. Moderate earthquake around 500 years, and the severe earthquakes around 2500 years. But all these definitions of the earthquakes and also the damage, the performance is not always guaranteed. These are some of the photos which shows that the current design provisions are not adequate. Not in India, in all around the world. All these buildings or structures have been designed following the current code of practice, either response vector method or equivalent force method. But during the earthquake, you can see there is a severe, collapse of the structure. So what are the drawbacks? The drawback is like it doesn't mean that like all the code provisions are wrong. The code compliant buildings have performed well in some cases, but many cases the performance is not good. The second problem is like when you do the retrofitting and existing retrofitting of existing buildings, to what level we have to retrofit it, because the same building was designed, the same structure designed for the code, and what they kind of resulted uneven performance. The performance, I expect that my beam should damage, but in most of the cases the columns are failed. So the performance based design actually try to answer all these questions. The current design provisions, where you would try to calculate the design base shear and then you distribute the design base shear over the height by equivalent static force method or response vector method, are mostly kind of a force-based approach. You first calculate the force and then you design the structure. But actually, like if you try to see the responsive structure, the responsive structure is more a kind of a related to displacement. For example, like if I take a column and I apply 100-ton load on this lateral load, maybe 100 kilonewton load, probably it is very difficult to say that whether the structure will or that column will damage, if it damaged to what extent. But the same structure or same column, if I say that I have a load which creating a displacement of, let's say, 1 meter. One can say, oh, 1 meter displacement is not possible, so its structure is collapsed. So damage defining in terms of displacement parameter is a better alternative than based on the force. So the performance-based design is more towards a displacement parameter and is mostly called as the displacement-based approach. The objective of the performance-based engineering is to design a structure to get some specified results. For example, I designed the structure to get a drift of 1%. I'm talking about inelastic drift. But your current code will not tell you that if you design the structure, what is the drift you are going to get. So rather than following some set of guidelines, prescriptive guidelines, you design the structure to get that drift. You design the structure to get that yield mechanism, strong column, weak beam. So the performance-based design or performance-based engineering actually started from a project of retrofitting and strengthening. It is more detailed one. It's little complex, but it's not that complex which can't be actually implemented. So the simple words, the performance-based design is to design something for the achievement of specified results. If you say that like design this building so that my top floor acceleration should not exceed 0.1 g. Can I do that by following the current design method? No. So that is where the performance-based design actually come into place. I'm not going to follow the prescribed means, but I'm going to design so such that I'm going to get the acceleration at the top floor as 0.1 g. Currently, although it started from the retrofitting or the rehabilitation project, the performance-based design is now kind of a meaningful tool to take some decisions. For example, whether the building need to be collapsed, demolished, whether the building need to be retrofitted, or whether the building need to be added with some new dampers. All these actually involve the cost, and that cost estimation probably you can't do using the force-based method. So the performance-based design is one of the tools is not only actually give you the expected seismic response, it also helps you to take a decision on whether to go forward for a specific project or not. That means the cost factor is also coming into picture. So there is a cost and the value. So it says a cost versus the performance evaluation. For example, like if I'm staying at a top floor, I don't want that the earthquake shaking to exceed some limit. I don't want, so my serviceability should not actually be disturbed. So if I define that parameter, that what is the maximum limit you can afford, and take that parameter and go for the design. So what I'm going to do here, there are several improvements or the generations of the performance-based design. I'll start with the basic one, and slowly I'll give you some idea about the recent or the developments of the performance-based engineering. If I follow the performance-based steps, there are mostly 5 steps. The first, you have to define the performance. I say that I need the displacement at this floor at this much. I need the acceleration at this floor at this much. I need this element during the earthquake should be damaged, and this element should not be damaged. And to be damaged to this extent or to damage to that extent. So that is how you define the performance of the structure. The second one is once I define the performance, I actually evaluate the approach, what approach I'm going to follow. Third, I do the analysis, the modeling, and finally I check that my acceptance criteria are met or not. What is the performance definition? In defining the performance definition, there are two things are important. What is input? What is output? What is input? Input is my earthquake, ground motion. What is output? Output is my how my structure is performing. So the input is related to the hazard, and the output is the performance, that is the structural performance, which is essentially a damage limit state. So when I associate a performance level to a hazard level, that means for a particular earthquake of this written period, my structure should not get damaged to that extent. That statement I called as the performance objective. And the whole performance-based design is based on that. You are clear what you are actually doing. If there is a design basis earthquake, and I have a 20-story structure, what is the maximum drift I am looking for or I'm expecting? What is the maximum acceleration which the structure will experience to? What is the maximum number of elements which will get damaged? Which are those members? And that is called the relation or the statement relating to the structural performance with a particular hazard level. Hazard is always input related to earthquake. Performance is always related to the structural response. That's called as the performance objective, and that is how we define the performance. Now I say the hazard. What is mostly the earthquakes are characterized by hazard curve, which essentially indicates the probability that for a given ground motion, it can be peak ground acceleration, it can be peak ground velocity, it can be peak ground displacement, that will be exceeded for a certain period of time. What is the probability that a PGA of 0.4 G would be exceeded in 50 years? So that is how we define the hazard. For example, there is earthquake having a probability of 2% of accidents in 50 years. So when it's the earthquake, that means I'm talking about, let's say, PGA or PGB or PGD. It's 2% of accidents, 10% of accidents, 50% of accidents in 50 years. So when I define this, automatically the probability of 2% in 50 years, if you do the probability analysis, we'll get the return period is close to 2,475 years. When it's a 50% probability of accidents in 50 years, which gives you around 90 or 100 years return period. Now, rather than defining that minor earthquake, major earthquake, moderate earthquake, I can always set what is the probability of accidents of that earthquake in 50 years return period or the 100 return periods. When I talk to the structural performance, it actually indicates some kind of unique or discrete damage states among all possible damage states in the structure or a building may subject it to during earthquake. For example, immediate occupancy. Immediate occupancy means there is an earthquake, hit that structure, and after the earthquake, the building is safe to be occupied immediately. Or let's say I call as the collapse prevention. That means the building has been damaged, but it has not collapsed, it is nearing collapse, just next to collapse. Or the damage such that the collapse is just prevented. Or life safety. That means the structure has been damaged to such an extent that it will not, again, it's not been collapsed, but there is a severe damage to the structure, but still with the repair and retrofitting, the building can be used. So in terms of performance objectives, again, it is related to the hazard and the performance. So there are four things which I'm going to mention here in terms of structural performance. If I say the operational, like everything intact. If the immediate occupancy, probably some of the non-structural points, disturbed or damaged, non-structural like your glass panel broke. But so that you can go, it doesn't matter, like it not hamper your structure or occupancy level. The building is safe to occupy, but probably like you need to clean up or some minor repair in the non-structural elements. Life safety, the building is safe, but probably you have to do little bit of retrofitting. Collapse prevention, the building is verge of collapse but not yet collapsed. You have enough time for the evacuation. Now, when I correlate this building performance to the hazard level or the shaking level, so I have operational, immediate occupancy, life safety, collapse prevention in terms of the structural performance, and in terms of the hazard, I have some kind of probability, like 2% in 50 years, 50% probability of, so that is the input. If I make a matrix of this, in this axis my structural performance, and this axis is my design hazard level. So it is when I define that probability of accidents in some kind of year, it automatically gives you the return period of the structure. For example, like there are 4 levels of the design checking I'm taking here. In some of the codes or guidelines, they go for 3, 5, but the correct example I'm saying, if there is an earthquake which has a probability of accidents in 50% of 50% probability of accidents in 50 years, or there is an earthquake with a 20% accidents in 50 years, or there is a probability with a 10% accidents of 50 years, or there is a earthquake 2% probability of accidents in 50 years. Each has some unique meaning. 50% 50 year, 20% in 50 years, 10% 50 year, and 2% 50 year. As you go down, the return period of these earthquakes actually increases. It's 2475, this is 475, and so on. So 50% probability, higher probability of accidents in 50 years, that is frequent, probably the occasional, rare, and very rare, which is we define as the maximum considered earthquake. And the rare earthquake, which we mostly define as the design basis earthquake. Now, if I go from the x-axis, you have the operational level, immediate occupancy level or occupiable. You have life safety or major damage, or near collapse or collapse prevention, right? Now, if I make a table or matrix A, B, C, D, like operational, frequent, or for the frequent earthquake operation, or for the frequent earthquake, life safety, or the occasional earthquake, let's say if I come to that, this indicates near collapse. So if what are the things which are acceptable performance objective as a designer? If I say that I have a very rare earthquake and the structure should be operational, if I come to M here, that means you are looking for a very, very exceptional structure. Nuclear plant, nuclear power plant, or the dams. Now, if I say that I have a frequent earthquake and is near collapse, very minor earthquake, my structure is collapsed. So this performance objective is not acceptable. Or I have a occasional earthquake and it's collapsed. So from this table, your design or performance-based design is actually evolved. So what we are mostly selected for the residential structures, Like if there is a rare earthquake, which has a 10% probability in 50 years, let's say, the structure should be life safe. That is, there is major damage, but it can be reusable after repair and retrofitting. And if there is a maximum considered earthquake, it's nearly collapse. So if I take these performance objectives, mostly the diagonal one, frequent, operational, A, occasional, immediate occupancy, rare, life safety, very, very rare, nearly collapse. That makes sense. Because very rare earthquake, we don't know whether the structure will ever explain that kind of earthquake. So why should I go for a design for life safety? So this diagonal mostly represent the design objectives or performance objectives for commonly built ordinary structures. If I go below this diagonal, for example, I'm looking for here maximum considered earthquake, operational or occupiable damage, or life safety. That means I am looking at little stringent performance objective. So probably I can use that for the critical structure. So if you see the EJO, this is more stringent than AFKP. Occasional, operational, or if I say that O is maximum considered earthquake, life safety, probably I am looking for a hospital building, a water supply facility, a telephone facility, telephone structures like this. If I go to a further down, that is maximum considered earthquake, you have damage, or rare earthquake operational, I'm going little more important structure. And if I am looking for only M, it's very, very important structures. So this matrix gives you a clear relation between which earthquake you are talking about, what is your goal. But if you go above this, like BGL, so you are looking at relatively flexible or lower category of performance, and sometimes it is not actually acceptable. The same thing I am actually showing here. So the diagonal terms is called the basic objectives. So very low earthquake, frequent earthquake, and fully operational. So probably like that makes sense. Here you don't probably look at the structural stability, but you want to check that whether all the serviceability limit states are satisfied or not. This one, rare earthquake, that is DB earthquake for 75 years of return period and life safety. This is the one which we mostly talk about in the code-based design. And here, so you design for this, and here you check the stability of structure, because near collapse doesn't mean the collapse. It's still standing. So you need to check that you design for this level. You check the serviceability is maintained for the frequent earthquake level. And the same design, you check that for the very rare earthquake, your structure is not collapsed but nearly collapsed. That means this state need to be checked for the stability, and this state need to check for the serviceability. So your design forces everything you calculated from this level. Similarly, like you see that these are for the essential services. These are for the safety critical, and this is very rare and fully operational. Probably you can go for very complicated and important structures, probably like is practically not feasible. Even the nuclear power plants are also like very rare earthquake, magnitude 9 or something. It has to be operational. Okay, again, it depends on like how you define the operational in terms of the building or the structures. But that is how this the performance objectives are defined. Now, just to give an idea in terms of the building, when I say the fully operational, that means none of the things are damaged. Probably anything between from here to here. So I can say like even if I'm here in the because it if you draw the force deformation diagram, first part is linear and the non-linearity starts. So anything below this, it's I can say elastic, so it is operational. Just at yield point or just after the yield point, if your structure is at that level, I can say this immediate occupants, which is very limited damage. And then probably somewhere here, before your ultimate point, it's called the life safety, and just before the collapse, that is your collapse prevention. And collapse is, of course, you can think that everything comes down, which is here. So in a realistically term, my operational limit is always elastic, which probably I don't care. Though three things, IO, LS, and CP is within the inelastic portion. So just after the yielding IO, somewhat near the ultimate or before the ultimate is something life safety, and just before the collapse is the collapse prevention. Just I'm trying to correlate with the concrete, let's say. When you apply earthquake load to a concrete building, you will see that the first thing you will notice is the cracking in the concrete. And the second thing is the reinforcement bar yielding. Third thing you will probably notice is the crushing of the concrete. And the fourth thing, the mostly important, is like crushing of the core concrete of the column and buckling of the bars, and then you have the which induce the collapse. So if you see that just below the yielding, probably like you can think of like it's a nearly elastic, and that stay in the stage limit your or indicate that is a serviceability case. Between the crushing of the cover concrete and probably the yielding somewhere here, you can see that it will be very minor repair is required. And when you have the crushing of the cover concrete, probably like you have the repair, you have extensive repair. And when you have the crushing of the core concrete of the column and buckling of the parts of the columns, it actually shows the safety of the structure. What happens to the lateral capacity? Till the crushing of the cover concrete, your lateral strength keeps increasing. It remains more or less same till you reach the crushing of the core concrete, where there is a decrease from the cover concrete to the core concrete. But after core concrete and bar buckled, you have a sudden degradation in strength. It means it's an unstable case, and then you have the complete collapse of the structure. Okay, as far as so this is the lateral capacity is concerned. But if you see the axial capacity more or less stable till this point, again it fails. But your lateral capacity, the moment your cover concrete crush, your lateral capacity start reducing gradually, whereas your axial capacity does not change that much. So that is how you define your performance objectives. Whatever the uncertainties, like I say, the 2% probability in 50 years. So there are uncertainty in the hazard definition, there are uncertainty in the structural prediction, because you say that like this part will provide, like this beam or this column will give you the plastic hinge. It all depends on how accurately you model your structure or how accurately you analyze that structure. So one can do a detailed nonlinear modeling, or some of the codes actually give a indirect way of doing the performance based design, even doing the linear analysis. But in that case, you need to have certain level of confidence, and typically 95% of confidence level you need that the structure will provide the collapse prevention or better performance for a particular hazard level. Okay. The second one is how to evaluate. So that is the performance definition. Now, the second one is how to evaluate the structure or how to achieve that. To do this, I say that you can follow a linear method or you can follow a non-linear method. Non-linear method is more accurate. It requires the significant knowledge of non-linear modeling and structural behavior. So one of the ideal way to find out the non-linear behavior is to do the non-linear dynamic analysis. Again, which is again very, very complex. So one of the best way to do this is do a non-linear static analysis. Although the earthquake ground motions are or the hazard you are looking is dynamic, but non-linear static analysis give you a lot of information. It's relatively easier to perform. And what is the non-linear static analysis? It's also called as the pushover analysis. That means you have a structure, you push the structure monotonically either to the left or to the right and do a displacement based analysis. Displacement based analysis means you push the structure assuming that the displacement at this level will be, let's say, 1 mm, and look at what are the stresses and what is the state of all the members. Increase to 2 mm, find out that same. 3 mm, 10 mm, 20 mm, 40 mm, 50 mm, and till it collapse. So what you do is you apply some displacement here and you measure that what is the resistance of the structure, nothing but what is the base shear of the structure. So the pushover curve is simply a curve representing the lateral strength, which is nothing but your base shear. Lateral strength means it's a base shear of the structure versus the roof displacement. So from this curve, which is the capacity curve of the structure, you do a monotonically increasing displacement loading step by step, and you try to visualize how each member and the structure as a whole they are performing. Now, one can ask, like, you are doing a dynamic analysis, you are dealing with dynamic loading and you are doing a static analysis. What is the relevance of this? The relevance is like it's called the equivalent inertial effect, because you know that when there is dynamic loading, you have the inertia force. And so when you do the pushover analysis, in a sense, you are applying the equivalent inertia force at each level that corresponding to some kind of dynamic loading. And you are trying to visualize and trying to find out how each member of the structure and how structure as a whole they are performing. The pushover analysis gives you a lot of information. It first gives you what is the maximum strength the structure can take. If I have this curve for the particular structure, I do the pushover analysis. The maximum load it can take, lateral load. It can also give you what is the point where the yielding will start in this structure. It gives you what is the stiffness of the structure. It gives you what are the elements which are going to be damaged and what is the sequence of damage in the structure. Where are the location where the plastering will form. Plastering is nothing but is the damage. Either is the flexion, shear, or combination. So the pushover analysis means you apply equivalent lateral force and find out the displacement. Again, it's not force. It's a profile you apply. Then why I'm talking about the profile here? You know that there is a mode shape in the dynamic analysis, right? Each structure, if you do the eigenvalue, you will know the fundamental period and the mode shape. So that means a structure under depending on the stiffness and the mass, and the distribution of the mass, it will give some particular nature of the vibration shape. That's what we call as the mode shape. So essentially, it's not exactly mode shape. Mode shape can be one of the option. Essentially, you try to apply a displacement profile which is consistent to the lateral forces or the mode shapes. For example, like if you say that I am providing a lateral force, if I have a base shear, you try to distribute the lateral forces. So what do you say? You will get a 50 here, 40 here, 30, 20, 10, 5. You get some profile, like if it's a parabolic profile or a linear profile. That is the force you get, like if you follow the equivalent static method. So here, you don't apply the load, you apply a displacement profile. For example, like if I apply 10 mm here, what is this floor is moving? So I can assume that profile is a parabolic, and then if it is a 10, it is 0, I can apply that profile only. Keeping 10 here, then automatically if I define that profile as the parabolic or linear, it will calculate what is the displacement here, what is the displacement here, what is the displacement here, what is the displacement here. So what, in a sense, you apply maximum displacement here, or you apply profile with maximum roof displacement 10 mm, which corresponding to, let's say, this, and then you get a, then you increase 10 to 15, keep the same profile. That profile may be consistent with your lateral force distribution, or that may be consistent with your mode shape. It can be anything. So, but it has to be consistent with your structural performance or loading condition. When I say the mode shape, it is the structural performance. When I say the loading condition, probably your lateral force distribution over the height of the structure. So, and then you do step by step. You increment, gradually increase. Let's say start from 0, apply the roof displacement 5 mm, and then if you know what is the profile here, or if you assume some profile, let's say linear profile, you can automatically find out what is the displacement here, and then for that loading condition, you find out what is the maximum base shear, what are the casting hinges, all these things. So what you do here is, in the nonlinear static analysis or pushover analysis, you first model, like mostly you are using the ATALs or the SAP, which are pretty good softwares. You first model the beams, columns, slabs, whatever you want, the 2-dimensional or 3-dimensional structure. But when you do the pushover analysis, it's important that you define the force deformation behavior of each member. It is not defining only the E value and Poisson's ratio. In STAT analysis or in SAP analysis, when you do the linear analysis, probably the only two parameters you give, what is the E and what is the Poisson's ratio. But when you do for the nonlinear analysis, you have to give their expected behavior as the input. What is the expected behavior? Irrespective of that how a column or beam going to fail, you have to consider all possible modes of their failure. For example, a beam may fail in the shear or flexion. Similarly, a column may fail in shear or flexure or axial. So you have to understand that if a beam fail in flexure, how the flexural force deformation curve will look like. For example, like if you take a simple supported beam and do in a lab apply the 2-point loading or maybe single point loading, keep on increasing the loading till it collapse, and look at the curve, probably force deformation curve or moment rotation curve. You will see that there will be a linear curve and then followed by something, so if you try to do a test, what you will say that they are linear, and then probably it will go like this. If the same beam actually fails in shear, what you will see that it will just keep on increasing and suddenly fail. So this is a flexural failure, this is the shear failure, and I don't know how this, any of this member will fail. I have to define this shear behavior and the flexural behavior along with their interaction in my program. To do this, FEMA 356 is one of the best standard. FEMA 356, somewhere I have mentioned. Yeah, you can see here. It gives you a very simplified version of your actual behavior. Now, if it is a linear and non-linear, I can model that it is some kind of a series of linear curve. So you can see one linear, then strain hardening, then degradation, and the residual strength. And this is the one which you can see here. This is the linear elastic behavior. Then there is strain hardening. This is the yield point. This is the ultimate point, and then the degradation and the residual strength. This is a flexure behavior. Now, this is a unique curve which can define the flexure behavior and the shear behavior. If I say the flexure behavior, I have some kind of ductility between yield to ultimate. In the shear behavior, my B and C will be in the same point. So if I say that A equals to 0, the same curve can be implemented. Okay. Now, each member has their own different member properties like geometry properties or the different reinforcement detailing and different moment capacity. So it's always, the code always gives you a normalized form. That means you normalize with respect to their yield strength in flexure or the shear, and then you simply define this curve. And since it is easier to find out the theta y or delta y or my or fy, you just define that. So that means what I'm saying that each member need to be defined some flexural plastic hinges, shear hinges, and the interaction between the axial load and the moment. So now the question is, what is that hinge? So if you see that member, you know that let's say this joint is a hinge joint, rigid joint, and if you apply the lateral load, the bending moment will be something like this. So maximum bending moment is here. So that means my plastic hinge will form here. It's similar to your structural analysis of analysis 3 when you do the plastic analysis. So you take a cross section and you define that here there is a hinge or there is a point where the force deformation behavior will be like this, right? Something like this. Something like this. And the same point you can define the shear hinge, because the same beam can fail in the shear. And same point you have to define that if you know that like if you have a beam, there is no axial load, you may get this kind of behavior. But if you apply the axial load and do the lateral loading, the curve will be something different because of the axial loading, right? So you have to give that interaction, axial interaction behavior at the same point. So what you do is you define some hinges at both ends. Ideally, one should define the hinges all around. Maybe like if you say that total length is 1 unit, probably actually 0.1, 0.2, 0.3, 0.4, 0.5. You have to define, flexure hinge, shear hinge, axial hinge, and the interaction for all these members, irrespective of whether it is a column or a beam. Now, if you do that, now the question is, what should be this point? What should be this point if you don't have the data, test data? So FEMA 356 actually gives you the parameters, whether it's a beam in flexure or column in flexure for concrete and steel. This is for the structural steel component. Similarly, if you go to table 5.5 or 5.6, you will see that will be for the concrete structure. It always gives what is this A should be, what the B should be, and what should be this C. All these parameters he actually gives you to model this. Once you model, at the same time, it also gives you that what should be the acceptable performance. That means what is the parameter in for a rotational parameter for beam for the immediate occupancy, life safety, collapse prevention. It is a primary component and the secondary component. For example, like you can see, for example, it gives you this point corresponding to IO. This is for primary and secondary. This point corresponding to life safety. This point corresponding to the collapse prevention, and this point probably like for the secondary elements. Secondary means non-structural elements. So if you do the pushover analysis, first the modeling. Once you do the modeling, keep doing the incremental loading, you will get this kind of curve, and at any point you can find out the hinge status. And if you see that like this point is something which is collapse prevention point should be this much, let's say the displacement of 25 mm, but your pushover curve giving a collapse displacement of 20 mm, the last displacement 20 mm, that means the structure is not satisfying the acceptance criteria of the FEMA. So that means you have to revise, you have to increase the section, you have to increase the reinforcement. Okay, so indirectly you do the iterations to satisfy the performance objectives of IO, LS, and CP. One not necessarily one should follow this. One can have their stringent rule. For example, this says that this should be 6 times theta y. I can say no, why 6? My life safety should be limited to 5. So I will design, analyze in such a way that my life safety should be 5 or 6 or whatever it is there. So once you do the pushover curve, in addition to this, it actually gives you a lot of information as far as the performance-based design is concerned. I say that you can calculate the stiffness. Now, ideally, you will not get a smooth curve like I'm showing here in the pushover analysis. Particularly if you're following the SAP. So it will be since I said you apply 10 mm, 15 mm, 20 mm, 25 mm, like this. So you will get one point corresponding to 10, 15, 20, like this. Now from this, one has to find out what is the yield strength. Now, since the linearity, nonlinear starts from here, people take this as the yield point, but the FEMA is not exactly yield point. You have to find out the yield point based on an idealized curve. So one of the way to find out the yield strength is not from this curve. This might be the initial yielding, but this is not the yielding strength of the structure. So one way is you draw a linear elastic line, and from the peak strength, you draw another line. Wherever it cut, you will get the yield strength. Now, how to cut this? Sometimes, like you have to see that how many area you are, or what is the area you are losing here, or what is the area increasing here. So, in a sense, it gives you the equivalent stiffness, and it also gives the equivalent fundamental period from, following some equations, for example, like this. Now, once you get this equivalent time period, why it is necessary that it is related to something called the target displacement. For example, like this is the curve I get. How do I know that it satisfies my performance criteria or not? So there are two approaches. One is called the displacement coefficient approach, where you calculate a displacement called the target displacement of a structure. The target displacement is simply like, if you remember, SD is equal to omega square, SD equals to SA, and SA you get from your code. and you only thing is you divide, that omega square to get the SD. Now that is your target displacement. That is the dynamics linearity, but these are some constants. So if you see the SA by omega square, it becomes your SD. So your target displacement is not something else, is the SD, and with some correction factors. What are the correction factors? That relation omega, SD is equal to SA by omega square. It's for a linear single degree of freedom system, but your structure is a non-linear multi-degree of freedom system. So you have one correction for single degree of freedom system to the multi-degree freedom system. That is a linear system. It is a non-linear system. So it's a C1 gives the relation between, if you know the linear elastic system, what is will be the expected in the elastic system. That your structural dynamics based on bilinear curve, right? Here actually you may have some kind of degradation in your hysteretic. For example, like your hysteretic response, it is a degradation. So C2 represent the effect of the pinching or the hysteretic loops, and C3 represent the P delta effect. You have a structure, the P delta effect actually governs, due to gravity load, you have the P delta effect. So in this method, in performance design, the first you comes from the dynamics, that you calculate. If you have a linear system, you calculate the SD and you multiply C0, C1, C2, C3 to represent a displacement, or to find out a displacement which will be realistic for your multi-degree of freedom system or multi-story building you are dealing with. Now, if this target displacement 20 mm and your structure or your base pushover curve gives a maximum displacement 15 mm, that means you didn't reach the target displacement of this, so you have revised the design. That doesn't satisfy the requirement of the performance based design. Okay, so this is the concept. I'm not going to highlight this more or less. I have already explained. Omega square SD into SA is for this system. You are dealing with a multi-degree of freedom system, that is C0. Your you have different kind of hysteretic behavior. This is for concrete, this is for steel. So you actually try to idealize in a rigid plastic model. So that's why you have to C2. Then you have C1 is for the linear system to non-linear system, and then C3 is for the P delta effect. Okay. So this target displacement, again, you can say the target displacement corresponding to CP, target displacement corresponding to LS, target displacement to IO. And if your pushover curves actually meets that or higher than, or if you get a lower IO or lower CP, that means your structure will fail prior to your target displacement. Then you have to revise. Okay, and that is what the based on which this acceptance criteria has been defined. So in the pushover, once you do the pushover curve and you directly can, if you add up this, you can directly check that whether your pushover curves actually gives you this, or your capacity of the structure is higher than these values or lower than these values. For example, like your beam collapse prevention 8 times theta y, whether you are reaching that or not. So this is for the member, and this target displacement is for the total structure. So you check both, one for the whether your structure is meeting the target displacement or not, whether your each member, beam and column, they are meeting their CP or LS or not. For what is the difference here is probably like your structure may meet the target displacement, but one or two beams they may fail. That means they may exceed the you need acceptance criteria of 8 times theta y corresponding CP, but the displacement they are actually sustained is 10 times theta. So that means those members are actually already collapsed. So what you have to do, you have to go to those members and only redesign those members. Okay, so that's why, like, if the performance based design based on this concept takes care of both each member behavior and as well as is the structural behavior. The other one is the capacity spectrum method. This is another method for the performance based design where you superimpose the input hazard curve with your capacity curve. Again, the capacity curve you get from the pushover analysis, and then superimpose with your uh, you know design response spectrum curve. Wherever they cut, that becomes your performance point, and that is the thing where you get the called the performance design, where the demand curve and the capacity curve meets at the point. I'm not going to explain in detail what is the capacity spectrum all about, but to be related to the dynamics, the only thing is the you do the same pushover analysis and you get this capacity curve, which is the force versus displacement relationship, like base shear and top flow displacement. The top flow displacement you have to actually convert to spectral displacement, and the y-axis you have to convert to the spectral acceleration. Okay, so like the base shear and roof displacement, you have to actually convert to the spectral displacement by the relation with SD equals to roof displacement by mode participant factor by the mode shape, the corresponding to 1. So you get the each value, you will get the spectral displacement, and then this base shear you have to divide by W, and the alpha 1 is the participant factor again corresponding to the mode 1, because everything you are going to the remember the pushover curve is the capacity curve for the multi degree of freedom system. You need to convert this to a single degree of freedom system. That is how your partial set, participation factor will come in picture, right? So you the entire multi degree of freedom system you are actually converting to a equivalent single degree of freedom system. Now, once you do this, that is called the capacity curve in spectral acceleration and spectral displacement. Now, once you do this, the second one is you have to calculate the equivalent viscous damping. So you have, capacity curve. Only thing is you have changed the x and y axis, and from this you find out the, bilinear curve, like to calculate the what is the stiffness, and from this, the ATC actually gives you that how to calculate the equivalent viscous damping for this structure, and which is nothing but the area ratio of the area enclosed in the force deformation curve. Okay, so why it is necessary? Because your spectral displacement curve, if you remember, the hazard curve is a function of, you say that the response spectrum curve with respect to what damping, 5% damping, 10% damping. That's why from this you need to estimate what is the equivalent damping parameter, because when you superimpose this curve should be consistent with this damping parameter, not 5% damping. Okay, so same thing you do for the demand spectrum curve is easy. You can remember I've shown you that this is the hazard curve given in your code. The only thing is SA by G by time, and I know there is a relation between time, SD and SA by this. So I can replace this time by spectral displacement, and I can draw this, and where this line will represent my initial time period. Now your capacity curve in this axis, demand curve is this axis. Now simply you superimpose. When you superimpose, you have to make sure that your curve, the demand curve, must be consistent with your damping curve, equivalent damping curve. And wherever it cut, that gives you the performance point. Okay, so mostly that is what the procedure is follow like this. You first initially design a structure, because when you do the pushover analysis, you have to define the member sizes. So approximate design you have to do, And then you do create a numerical model, do the nonlinear static, or you can do a nonlinear dynamic analysis also. And then you compare with your target displacement or capacity and demand curve, check that whether it's satisfied or not, or do the iterations to satisfy your. So for example, like if your performance point is something is here, that means your curve actually meeting like something like this, that it shows that your structure is highly is elastic. That means your structure is very strong. So you need to have, so that also gives you to iterate the structure to get the performance at the same time saving the cost. Okay, there are some linear analysis procedure also, linear analysis method, because that is pushover analysis is non-linear analysis. In the linear analysis, more or less the similar thing. The only thing is that you calculate that pseudo lateral force, and you try to find out for each member when you do the linear analysis instead. You try to find out that what is the force coming to a member and what is the capacity of that, and it's only changed by some kind of factors which is called as the confidence factors and some kind of amplifications the code defines for different members. So it's not that the performance based design can't be done in the linear analysis, but it is a very approximate. So that's why in the performance based design, the non-linear analysis is the one which gives you a more reliable and robust result. So in linear analysis, just to check the demand and capacity of the uh, amplified demand versus the capacity of the structure. But one can also do for anything like the interstory drift or axial load or the any parameters. But here, when you do the linear analysis based performance based design, your confidence level must be more than 95%. So that is what it actually gives you the minimum confidence level. For example, like for the collapse prevention, at least 90 or 95% for the global behavior, and for the immediate occupancy, that it should be the 50% recommended level. Okay, so that is how you calculate the demand capacity curve, and it takes into account a lot of parameters related to the analysis, related to the demand variability, and also the partial safety factor. If you remember the capacity factor, that is your gamma, it's taken into account. I'm not going to detail in this because mostly the performance based design which is being done or which is being implemented or coming in the your upcoming IS 1893 is based on the non-linear analysis only. Okay, what is the correct current direction of the performance-based analysis engineering? It is mostly the previous part is only to define the hazard curve and the performance level. Right now, it has been extended to that, can how much percentage of cost I can save. That is the, and what is the downtime and how much time it will be. So all this time and cost analysis has been implemented in the performance based approach. So again, which is the probabilistic in nature. But here what you do is you take the decision variables. Actually, it depends on what is the cost, what is the downtime, what is the damage measures you have to take, what is the main demand parameters, whether it's the force, displacement, or acceleration, and then what is the intensity measure, like what analysis or hazard curve I have to take. I'll just skip this one. I'll just try to show this how it is done. Mostly it is expressed, is called as the incremental dynamic analysis, where the same structure you do the a series of ground, time history analysis till it collapse, and from that you try to find out the median one, and for the collapse performance you try to find out what will be the design or expect. So it's a kind of a reverse engineering. You first do the increment dynamic analysis, and from that you estimate that how much cost and what is the downtime if the structure is going to collapse or maybe design under seismic loading. So that is what we call the seismic damage fragility curves. For example, like if I need that my displacement should not exceed 2%, then what would be my probability of failure? What will be my probability of failure, like for let's say different damage state? So I can create a series of fragility curves, and that based on that I can decide that which one I have to implement in my design based on the requirements. Okay, I think I will stop here. So already I have explained nonlinear Pushover analysis. If you have some questions, we can uh, discuss that. Yeah. Any
questions? Any questions from the participant? Sir, there is in chat box question from Ankit. What is the difference between FEMA 356 and ASC
same
41
same
criteria?
exactly same? No, not so. Essentially, in 2000, FEMA 356 came up, and mostly the same thing actually become a code of ASC 41. What will the advantages of using IDA or pushover analysis? How do you get the yield strength by doing the IDA, incremental dynamic analysis? Incremental dynamic analysis is only done to determine the fragility curves. Otherwise, to calculate the yield strength and all these things, you have to do the pushover analysis. Incremental dynamic analysis is a series of time history analysis. Okay, mostly done to do the collapse assessment of a structure. So it's a more or less as I said, like we always design the structure for the design basis earthquake and check the stability for the maximum considered earthquake. Incremental dynamic analysis is you keep on increasing the time history, PGA or spectral acceleration till your structure collapse, and from that you get a confidence that what is the earthquake which is going to or a probable earthquake or probable PGA which will cause the complete collapse of the structure. So that is the and then based on that one can find out that it's a 20% probability to collapse or 30% probability to collapse. And then once you have series of fragility curves, uh, one can it makes more sense to decide which design philosophy I have to follow or which members I have to strengthen. So it's a one step ahead of your conventional performance based design. You can follow either of those Mander or Kent Par. Um, I would go by Mander, but Ease has some limitations. But mostly, sometimes I follow Mander's model, sometimes I follow Kent and Park model. Both are equally good. Both have their own limitations and advantages.
There is one question, sir. What is the best confinement model to be okay?
Yeah, I have that answer.
Yeah,
So
you
the
have to
history model for the concrete, uh, I think Takeda model is for the concrete, and for if you are following steel structural steel, I think the combined hardening or maybe kinematic or isotropic hardening should be fine. But for steel, as for concrete, I will always go by the Takeda model, unless it is a ductile detailing, the very well detailed. Uh, and there I can skip the Takeda model, but in general, for complete Takeda model is preferred. It depends. You can use any of them, lateral load pattern or mode shape or acceleration based. But if you ask me, I always prefer to go by the mode shape method as the pattern for the pushover analysis, because the mode shape is more related to displacement rather than the force pattern. So I will always prefer the mode shape, but you can choose any of them. Mode shape is more realistic to me. Anything else?
Any questions? Is
Uh, um, so that's a good question. Integrate the performance-based design to the prescriptive mode. Um, it can be done. It can be done. The only thing is like we need to find out a realistic or simplified way for the pushover analysis, but it can be done. Integrate the performance-based design to prescriptive design method. If you don't get the first mode shape or the pushover analysis, then simply go by lateral force distribution. That should be okay. Yes, the answer is yes. Yes, we can use the performance-based design for the composite structure. In fact, it's in some of the codes, it is mandatory. Japanese codes, it is mandatory to go for the performance-based design for the composite structures. Any other questions?
any other questions?
Excuse me, I'm from architecture faculty. So, what should be the plan form and build form has to be considered to withstand the structural symmetry and ductility,
What should
etc.
be? I didn't get you. What should be?
What should be the plan form and build form? Because in 2001 earthquake, uh, the Bhunga house has been saved near the Bhuj earthquake epicenter.
Mm-hmm.
So we are from not structural civil engineering, we are from architecture. So for architectural students, I am going to teach. So plan form and build form is how the structural symmetry can be created so that minimum damages can be occurred during the earthquake.
Uh, I probably I don't have a direct answer to this because I probably are not uh, see the basic concept is probably like to limit the damage is the probably the regularities. If you can get away or limit the regularities in the architecture and
Okay.
also yeah, so that is one of the way whether it is because the more irregular the structure is, more complicated the behavior is, and whichever the model you do,
Yeah, yeah.
many times
Yeah, I mean,
we are not able to capture the behavior.
okay, okay, okay.
Yeah, so
Thank
see
you.
the basic concept is like you should have a where continuous load path. Like if you are, you think of like if you are applying a force at the top of the roof, then there has to be a continuous load path so that that load will be transferred to the footing in a continuous path without many discontinuities in between. And then if that is taken care of, probably like you know the most of the problem is solved. Of course there will be some kind of torsion or something for the irregular structure, but the load path is the one which need to be taken care of very very seriously.
Okay, because we used to tell the plan form, circular plan form or polygonal plan form, and through Bhunga house, which has been saved during the Kutch earthquake, so cylindrical and conical roof form has been adopted in the traditional architecture. and
Yeah.
that village has been saved during the earthquake. And through that, we have got the motivation to teach the architectural students and learn by myself also. That kind of plan form and build form, which is going to make the equivalence of the counterbalance of the forces which has been generated during the earthquake.
Yeah, the conical, if you ask me the conical one, that would be a much better option. But if you,
That's why I'm asking whether, because you are the expert,
yeah,
and that's why I want to take the opinion from you, because that's why I'm attending this FDP.
yeah. So that is the best option. But as you know, like these days, we are more fascinated to provide. Like if you see the
Ah,
conical
yeah,
one,
yeah,
your free space you are living actually. Like so, it's the other way around. It's the inverted conical. We guys are actually right now. You are building the structure. Like we use the minimum ground space area, whereas the top floor is as maximum as possible. So inverted one
yeah,
was not recommended. Yes, the conical one is definitely fine, but I don't see any problem if you are going for a cylindrical one or polygonal one. Those are very regular structures. I don't see why there should be any concern if there is no discontinuity between the floors. Otherwise,
yeah,
my understanding, circular one and the polygonal one, maybe a hexagonal or whatever it is, they are the best
yeah.
options.
Of course, sir. Thank you. Yeah.
Yeah, so the future Indian course with regards to PBSD, yes, performance-based seismic design is coming up in the IS 1893 edition. Displacement-based design will take some time, but definitely the performance-based seismic design that is ready already. It's under review now, and it would be reflected in the IS 1893 to my understanding, around July 2022, if everything
Mhm.
goes well.
Okay, sir. Thank you. Thank you, sir.
Thank you.
More questions?
Okay,
Any more questions?
I don't see any questions. Any questions,
Yes,
please?
sir. Yes, sir.
I'm happy to see that a lot of questions are there. Yeah, so regarding sharing of the some of the references, I will check because I have taken some of the pictures from somebody else. So my slides I can always share. And when I have taken some pictures, there are nowadays copyright problems. So I'll see that how many of these slides I can share with you. Okay.
Yes, sir. Yeah. Thank you very much, sir.
Yeah.
Sir, on behalf of AICT ATAL FDP, I thank you very much for sparing your valuable time for these two sessions. Thank you very much, sir.
Thank you, Aruna, and thank you for giving me a chance to interact with the participants. And it was a really very interactive session as far as the question answer is concerned. And wish you all the best.
Yes, sir. Thank you very much, sir. Thank
Thank
you.
you. Thank you.
So we will meet in the
Thank you, sir.
next session at 3 p.m. We'll have a lunch break, and after that we will meet at 3 p.m. Thank you all the participants. We are leaving the meeting.